Welcome all. Today we will start with the next part, that is counters. Counter is used for counting pulses, which is called as a counter. It is a group of flip-flop with clock pulses applied to it. Counters counts the number of clock pulses. Therefore, with some modification we can use the counter for measuring the frequency or a time period of particular operation. Basically there are two types of counters: asynchronous, which is also called as a ripple counters, and synchronous counters. In asynchronous counter, external clock signal is applied to one flip-flop and then output of previous flip-flop is connected as a clock input to the next flip-flop. Because of this, in asynchronous counter, all the outputs of the flip-flop will not change simultaneously, whereas in synchronous counter a common external clock pulse is applied to all the flip-flops involved in a counters simultaneously. Therefore, outputs of all the flip-flops in synchronous counter changes simultaneously. Now we will see the classification of counter. The synchronous and asynchronous are the types of counters. In both we can have up counters, down counters, and both up down counters. The up counters are the counters that count from small to big count, means they count in increasing order as they receive the clock pulses. For example, the output of an up counter will be 0, 1, 2, 3, like this. Whereas in down counters, the counting starts from large to small count. That is, the output goes on decreasing as they receive the clock pulses. For example, the output of down counter will be 7, 6, 5, 4, 3, 2, 1, 0 in this order. Whereas the up counter is the combination of both up counter and down counter, means it will count up direction or in down direction also. Now we will see first the asynchronous up counter. From that we are going to see a 3-bit asynchronous up counter, which consists of 3 flip-flops: flip-flop A, flip-flop B, and flip-flop C. Basically in this a JK flip-flop is used, in which J and K, both the terminals are tied together and connected to logic 1 signal. As we see, a first flip-flop, that is flip-flop A, has external clock pulse, whereas the second flip-flop, having a clock input of previous output of flip-flop A, this flip-flop C is having clock input of previous output of flip-flop B. Each flip-flop is a negative edge triggered flip-flop, means their output will change at the negative edge of the clock pulse. A clear input is connected, which is of logic 1, to all the clear terminals of the flip-flop, and preset terminal is also connected to the logic 1, means there is no effect of clear input and preset input, as the clear and preset terminals are active low signals, and we have connected a active high signal to them. And these are the three outputs of the flip-flop QC, QB, QA, in which QC is a MSB bit whereas QA is the LSB bit. Initially, before we see the operation of the asynchronous up counter, we can consider the outputs of all the flip-flops in a reset condition, that is QC, QB, QA is equal to 0, 0, 0. Now we will see the operation one by one. Before the application of clock signal, the outputs we have considered as a 0, 0, 0. So QC is 0, QB is 0, and QA is also 0. Now, as soon as the first negative edge of the clock pulse hits the flip-flop A, as the J and K inputs are connected to logic 1, flip-flop A will toggle now. Hence, the output QA will change to 1, which is previously 0. Now, the QA is connected as a clock input to the flip-flop B, and as QA is changing from 0 to 1, means the clock pulse will be like this. This is the logic 0, this is the logic 1 level, this is the logic 0, and this is the logic 1 level. Now in this case, QA is changing from 0 to 1, means the flip-flop B receives the positive edge of the clock pulse. Therefore, its output will not get changed as it is a negative edge triggered. So this 0 will remain as a 0 itself. Now the QB is connected as a clock input to this flip-flop C. As QB has not changed, it is a 0, means this 0 is considered as a negative level. Therefore, output of flip-flop C will also does not get changed, as it is also a negative edge triggered flip-flop. So QC will remain as it is, that is 0. So after first negative edge of the clock pulse, we can have the flip-flop outputs as 0, 0, 1. The initial values are 0, 0, 0 before the application of first negative clock edge, and after the first application of first negative edge of the clock pulse, we will get output as a 0, 0, 1. The initial condition is numbered as a state 1, and the output status after first negative edge is numbered as a state number 2, and their respective decimal equivalents are written over here. So after first negative edge, we get the output as 0, 0, 1. Now we will see what will happen at the second negative edge of the clock pulse. Before that, we will write down the outputs of all the flip-flops before the application of clock pulse. Here QC is 0, QB is also 0, and QA is 1. Now as soon as the second negative edge of the clock hits this flip-flop A, the output of flip-flop A gets toggled, means this 1 will become as a 0. Now the clock signals are like this. This is logic 0, this is logic 1, this is logic 0, this is logic 1, and so on. Now here QA is changing from 1 to 0. The 1 to 0 transition consists of negative edge of the clock pulse, which is over here. So As QA is changing from 1 to 0 and it is applied as a clock input to the flip-flop B, the flip-flop B will also gets toggled, by which its output gets changed from 0 to 1. Now as QB is changing from 0 to 1, this is 0, this is 1, the flip-flop C receives this positive edge as a clock input. Therefore its output will not get changed, it will remain as it is, means it will remain as a 0. So after second negative, here not first, it is a second, after second negative edge of the clock pulse, we will get output as a 0 1 0. The state number is given as a 3 and its decimal equivalent is 2. Now we will see the operation at the third negative edge of the clock pulse, not first, at the third negative edge. Before applying third negative edge, we will write down the outputs of all the flip-flops. Here QC is 0, QB is 1 and QA is 0. So at the third negative edge of the clock, the flip-flop A outputs get toggled, means the 0 will be converted into 1. Now again I will draw a clock pulse over here, 0 1 0 1. Now QA is changing from 0 to 1, means the flip-flop B receives the positive edge of the clock pulse, therefore its output will not get changed, it will remain as it is, means QB will be 1. Now as QB is not changing, it is a logic 1, means flip-flop C receives a positive level of the clock pulse as it is 1, and we know flip-flop C is negative edge triggered, therefore its output also will not get changed as it is receiving positive level of the clock pulse, means 0 will remain as it is 0. So after third negative edge of the clock pulse, we will get output as a 0 1 1. This is written over here and it is named as a state number 4 and its decimal equivalent is 3. Now we will see the output at the fourth negative edge of the clock pulse. Before applying fourth negative edge, we will write down the outputs. QC is 0, QB is 1 and QA is also 1. Now as fourth negative edge appears or hits the flip-flop A, its output will get toggled, means this 1 will become as a 0. Again I will draw the clock pulse, 1 0 transition. The 1 0 transition includes negative edge of the clock pulse, therefore the negative edge is received by flip-flop B, by which the output of flip-flop B also gets toggled, means this 1 will become now as a 0. Again the QB changing from 1 to 0, means the flip-flop C also gets negative edge of the clock pulse, as 1 to 0 transition consists of negative edge, falling edge, therefore output of flip-flop C will also get toggled, means it will become now as a 1 which was previously 0. So after fourth negative edge of the clock pulse, we will get output as a 1 0 0, which is written over here, which is named as a state number 5 and its decimal equivalent is 4. If we see, the decimal count is increasing from 0 1 2 3 4 in ascending order, therefore this counter is called as a up counter, as it counts from smaller number to bigger number. Now note that all the outputs are changing their states, but changes do not take place simultaneously. Therefore this counter is called as a asynchronous counter. The same operation will goes on repeating for the next clock pulses, for the next negative edges, and the outputs will change their values from 000 to 111. After reaching the maximum count, that is 111, the counter outputs will become 000 for further negative edge of the clock pulse, and the operation repeats itself. This is the timing diagram of the 3-bit asynchronous up counter, which these are the three outputs of the counter, that is QC, QB, QA, and the counter output status is shown in this at every negative edge of the clock pulse. This is the state diagram of the 3-bit asynchronous counter, which consists of 8 states starting from 0, 1, 2, 3, 4, 5, 6, 7, and after the last state it will again start with the initial state 0. Now if we see, the number of states can be calculated using this formula 2 raised to n, where n is the number of flip-flops used in the counter. Here there are 3 flip-flops, it is 3-bit counter, so 2 raised to 3 will gives you 8. Therefore a 3-bit counter consists of 8 distinct states, and the maximum count of a particular counter can be calculated using this formula 2 raised to n minus 1. Now here, as it is a 3-bit counter, the value of n is 3, so 2 raised to 3 minus 1, which will gives 8 minus 1, that is 7, is the maximum count of this 3-bit asynchronous up counter. Now this is the 4-bit asynchronous up counter. The diagram includes 4 flip-flops. Instead of JK flip-flop, a T flip-flop is used over here, and T inputs of all the flip-flops are connected to logic 1. First flip-flop receives the external clock pulse, and previous flip-flops receives the output of previous flip-flop as a clock input. These are the 4 outputs of the flip-flops, and each flip-flop is a negative edge triggered flip-flop. The operation is same as that of 3-bit asynchronous counter. The only difference is it is of 4-bit, means counting starts from 000 and ends at 111. This is the truth table of 4-bit asynchronous up counter, which shows the counting from 000 to 111. After 15th negative edge, the counter resets itself and the counting starts again from 000. These are the decimal equivalent of each counting outputs, and this is the timing diagram of 4-bit asynchronous up counter, which shows flip-flop outputs QD, QC, QB, QA at every negative edge of the clock pulse. And these are the different states of the counter. Thank you.